In 3.9, we are looking at an introduction to what are called differential equations, and these are equations that involve a derivative, okay? Usually, and that's my definition right here, usually something that involves implicit differentiation, but not necessarily, okay? So to start with, just a quick review, differentials, remember in 2.9 we looked at differentials and used them for linear approximations, and that's where we separated dx and dy, and we looked at dy as the vertical change on the tangent line that is used to approximate the vertical change on a function, and then dx is the horizontal change on the tangent line, which is the same as the horizontal change on a function, okay? But really what we need to think about when we're thinking about differentials are slight, oops, don't know why that happened, slight changes in x or in y, okay? And if you remember, dy is equal to f prime of x, the derivative of x, times dx, okay? It's the same thing as if we had dy over dx, and then we multiplied both sides by dx to cancel that out. Or another way to look at it is, since this is the same as dy over dx, we could say dy equals dy over dx times dx, all right? And we still have the same thing. So either way, we're looking at the derivative times dx, that tiny slight change. Now here, dx is not going to have a numeric value, but we are going to use the differential, the algebraic representation. So for this first example, we want to, we're told that we have an equation for a function whose slope at any point is twice its x-coordinate. So we are writing that differential equation. We know that it's going to be a differential equation because the equation, the description of the equation is told to us in terms of its slope, okay? Instead of being told something about the values on the function, like x and y coordinate relationship, like x is 3 times y, so then 3y equals x, something like that. Here we know something about the slope. So the slope at any point, so at any value of x, is twice the x-coordinate, okay? So that means that we could say that we have the differential equation dy over dx is equal to 2x, okay? So the slope dy over dx for any value of x is twice that x-coordinate. Now, this right here is a differential equation. We want to write the equation of a function. So what we are going to do is we are going to solve the differential equation, okay? So here's the process for solving the differential equations. The first thing we want to do is we want to get dy over here, or really all of any y stuff is on one side by itself, and then all of the x stuff, including dx, needs to go to the other side. So I'm going to start by multiplying both sides of the equation by dx, and so we have dy equals 2x dx. Now, from here, this should look a little bit like what we've been doing in 3.8, when we did antiderivatives, okay? And so what we can do is we can apply an antiderivative to both sides of this equation. The antiderivative of 1, so there's a 1 right here, the antiderivative of 1 with respect to the variable y is y. And then over here, the antiderivative of 2x with respect to the variable x is x squared. Now, it's not just x squared and it's not just y, because if you remember, indefinite integrals have to have a plus c behind them. But here's the thing, we only need to add the plus c on one side. We don't need to put it on both sides, because if I said plus c, I could call it like plus c1 over here and then plus c2 over here, because they're not necessarily the same constant. Okay, we can't use just the same c for both of those. The very first thing I would do to solve for y would be to subtract the constant over here from both sides, and a constant minus a constant is still a constant. So we only need to put the plus c on the right side. This right here is the solution to this differential equation. This is called the general solution to the differential equation. Oops. Okay, diffie-q is usually how we abbreviate differential equations. If you hear someone in college talking about diffie-q, they're talking about the semester class of calculus that deals exclusively with differential equations. We are only looking at a brief intro to that, okay? Now, this is the general solution. Part B says find a particular solution where y equals 2 when x equals 1. So think about the graph of this because that's something we're familiar with. X squared plus c, y equals x squared plus c, we know that that is the family of functions. Y equals x squared is a parabola passing through the origin, but then with that plus c, it could be shifted, this is not great pictures, but could be shifted up or down anywhere on the y-axis, okay, depending on the value of c. What we want to do is we want to take it from a general solution and say, now which one of the functions that satisfies y equals x squared plus c will meet this initial condition. So this is called an initial condition when they give us a point. And frequently it's written like this, where it says y of the x value, so the function of the input, -1, is equal to 2. Oops, there, equal to 2. Okay, it could be written either way. They could just tell you the ordered pair, they could write it in words, or it could be written in function notation here. All right, so what we want to do then is once we have a general solution, we can plug this ordered pair into that and then solve for c. So we've got 2 equals -1 squared plus c, meaning that c is equal to 1. Okay, so our particular solution is y equals x squared plus 1. Okay? All right, and I did say that once we have a general solution, we can plug in the ordered pair to find the particular solution. If y is not isolated, you could actually plug the initial condition in as soon as you have an antiderivative and then rearrange and solve for y, and it's a little bit less algebra. I'll show you an example of that here in a second. Okay, for this next one, we are given y prime is equal to 8x plus 1 over y squared. This is the same thing as dy over dx. Okay, either notation is fine. The first thing we want to do, like I said before, is we want all of the y stuff on one side and all of the x stuff on the other side. So I'm going to start by multiplying both sides of the equation by y squared and by dx. So we get y squared dy is equal to the entire quantity, 8x plus 1 times dx, not just the 1, so make sure you use parentheses. Okay, so now we are going to apply an indefinite integral. The antiderivative of y squared with respect to y is 1/3 y cubed. Again, technically there's a plus c, but we don't need to write it on this side. Okay, and then the antiderivative of 8x plus 1 is 4x squared, power rule, add 1 to the exponent, divide by the new exponent, plus x plus c. Okay, and then from here, I'm going to solve for y because it doesn't give me an initial condition, so I'm just looking for a general solution. Okay, so I'm going to solve for y by multiplying everything by 3 and then taking the cube root. So I get y equals the cube root of 12x squared plus 3x plus c. Now something I want you to notice is that I didn't write 3c. If I put a 3c on there, it's the same function. It's the same family of functions. 3 times a constant is equal to a constant. So you can put 3c or you can just leave it in terms of c. One thing that I do want to stress with the constant though is you can't solve for y and then just stick a plus c at the end. You can't, it's not like with indefinite integrals where we get through it and then we think, oh no, we forgot the plus c, let's just go back and stick it on the end. Because here things can happen to the c and that changes what your family of functions represent. So for example, let's say that I forgot that and I have y equals the cube root of 12x squared plus 3x, and then I thought, oh crud, need a plus c, and I stick it on right there. These are not the same function, okay? So this one is not wrong, or this one is not correct. Make sure that you remember c at the first step with the antiderivative, and then whatever happens to the function needs to apply to c as well, okay? At this point, I would recommend you stop this and try the next example or the next couple examples, and I will pick those up in the next video.